Talk about constant versus not constant acceleration for a minute. The picture here shows us different velocity versus time graphs. Graph A is a decreasing velocity. The velocity is positive, but getting smaller and smaller and smaller. That means it's a negative acceleration. It's losing velocity every moment that goes by. But notice that the slope of the velocity stays constant. Now, acceleration is dv dt. That means dv dt is staying the same all the way through. There's no change in the velocity at all. It's staying negative the entire time. So in other words, graph A has some constant negative acceleration, like that. And that's graph A. That's the acceleration versus time indicated by line A. Line B is a constant positive acceleration in green. So it would look like this. It's not as steep as A, so it's a little bit smaller. Positive, but smaller in magnitude. And there's B. And you can visualize C has no change in velocity. Line C is zero acceleration. It would just be a flat line at zero. So this is what we mean by constant acceleration. Constant acceleration doesn't mean the car is not speeding up or slowing down. It just means that it's speeding up or slowing down at a steady rate. So constant acceleration looks like a flat line, a horizontal line on an acceleration graph. It's a angled line on a velocity graph. On the right-hand side here, we have a situation of non-constant acceleration. From 0 to 10, there's a positive acceleration. From 0 to 10, there's some positive acceleration. Then from 10 to 15, the velocity is constant. It's not that the velocity is 0. The velocity is 60, but there's no change in the velocity. That means the acceleration drops down to 0. Then from 15 all the way to 40, there's a constant acceleration. In fact, from 15 all the way to 40, the velocity just decreases steadily. And so from 15 to 40, we have some negative acceleration. So and then from 40 to 60, there's an increase in the velocity. That's positive acceleration. So there's some positive acceleration that happens on that portion. So this is our acceleration versus time graph. On the first stage, the thrusters are on, and it's gaining velocity. Then the thrusters turn off, and it just cruises for a few minutes. Then the reverse thrusters are activated from 15 to 40. And now it's slowing down, and then the velocity goes negative until at 40 minutes, it's actually heading backwards, a velocity of negative 40. Then the forward thrusters activate again, and it starts speeding up. So here it's just positive acceleration, then 0, then a negative acceleration, the reverse thrusters, and then a positive acceleration again. So there's nothing wrong with situations that have changing accelerations. It's just the most common situation we encounter is ones where the acceleration is steady. And so that's what we'll look at next. If the acceleration stays constant, there are some simple equations we can use to figure out things like how far does something move if it's undergoing a constant acceleration. The first such equation is about the velocity. It says that the final velocity is equal to the initial velocity plus the acceleration times time. Now, there are equations where you have to use your brain to derive. There are other equations that you can understand with just your eyes. And this is an equation that you understand with your eyes only. Acceleration is the change in velocity. So you have to take the initial velocity plus the rate times time to figure out how much the velocity changes. It's just like if you start with $20 and you get $15 per hour, you would take $20 plus your pay rate times time to figure out how much you're going to have at the end of the week. You just think with your eyes on that kind of equation, okay? Now, if you want to know instead displacement, then we have to use our brain a little bit. If I want to know how far something moves, delta x, then we have to do the integral of the velocity from, say, 0 seconds to some time t. And we did this with velocity graphs way back here. Given the velocity graph, we can find the delta x by doing the integral, which is just the area under the curve. So we can do it graphically, or it's nice to have just an equation to refer to that's more convenient. So I just have to plug in the velocity expression and integrate it. So I integrate from 0 to t. The integral that I have to do is the initial velocity plus at. And that's an elementary integral. It gives you v naught t plus 1/2 at squared. So now we have a couple important kinematic equations for constant acceleration. Remember, these are only for constant acceleration. If it's situations like a changing acceleration, like in the right half here, the right graph, you can't apply these equations directly. You can apply it piece by piece where the constant accelerations are there, but these are only when the acceleration stays constant. Okay, so this is the change in x. In other words, x at time t is equal to the initial x value plus v naught t plus 1/2 at squared. And that's our second very useful kinematic equation. So position versus time under constant acceleration looks like a graph of t squared. It's a parabola, in other words. This is every term we can understand in the graph. X naught is the initial starting position. So it's a rocket starting from the position x naught, and it has some initial velocity to it. So here's the initial position. V naught indicates the initial velocity. That is the initial slope of the position graph. So at t equals 0, it starts with some velocity, and that's the slope that it's starting with at the initial moment, right there. Like that. Now, if there were no acceleration, if a was equal to 0, then that t squared term would be gone, and the particle would just continue with its initial velocity. That's just the inertia law. That if there's no acceleration, no forces that act on it, it would just continue its steady motion in the forward direction. But with the acceleration present, then the velocity changes. And in fact, this graph, notice how the velocity, it starts off positive. The velocity starts positive, then it goes to 0 velocity, and then later on, the velocity is actually negative. The slope is now negative over here. So this graph corresponds to a negative acceleration, meaning the rocket started at this position, moving forwards with a positive velocity, but then the reverse thrusters come on, and it's moving forwards, but then slowing and coming back and speeding up the other way. Okay? So every term has a nice meaning: initial position, initial velocity, and then the acceleration describes how the velocity changes as the rocket travels.